Today's lecture will cover section 7.6, the low C line. As we already described in the previous chapter, section 6.3, we introduced the distributed circuit model for transmission line circuit. That is, a transmission line can be represented as a cascaded series inductor and shunt capacitor. So, as you have already seen, the transmission line is represented by a series inductor followed by a shunt capacitor, and followed by another series capacitors and another shunt capacitor, and continuously extended as the transmission line goes. And one question, can we simplify the circuit into simplified circuits that comprise only, say, one conductor, one capacitor and one inductor, like that? Can we do that? Of course not, otherwise the textbook will teach you how to do that, right? So then why can we draw the equivalent circuit? Why should we adapt the so-called distributed circuit? Because the transmission line circuit, the size, the length, the dimension of the transmission line circuit is comparable to the wavelengths of your interested frequency, because their size are comparable. So the wave or the signal that goes in the transmission line only observe the circuit geometry in front of it. It cannot forecast, oversees the circuits down below, far away from it. So it can only experience the impact, the effect of the circuits in front of it. All right. So you cannot simplify the so-called distributed circuit. The signal only experience the change in characteristic impedance, the change in propagation velocity, such as due to the change of material. So for transmission line circuits, one important characteristic is you cannot simplify the so-called equivalent model. So on the blackboard, to the right of the blackboard is the distributed circuit. You comprise series inductor and shunt capacitor. Nevertheless, this is also a simplified circuit by the assumption that the transmission line circuit is lossless, which means that no energy is dissipated on the transmission line as it propagates along it. Of course, this is not true. So any circuit that we can make in reality contains certain mechanism of loss. So in today's lecture, we will introduce the mechanism that provides or generates losses in the transmission line. So in general, there are two mechanisms. One is the only loss resides on the conductor that makes the transmission line. And there's ohmic loss. Due to what? Due to imperfect conductivity. Because even though that we know the conductivity of metal is relatively high, for example, the for copper is 5.8 times 10 to the 7th for its conductivity, but it's not infinite. So it still exhibits certain resistivity. So the ohmic loss is interpreted as resistance on the transmission line. And they are also affects the transmission line circuits in the form of distributed circuit. So every section you will observe a series resistance on each section. Now that represents the ohmic loss on the transmission line conductor. The other mechanism is the conductivity of the dielectric material that separates the two conductors of the transmission line. As you already know, that most of the transmission line configuration comprise two separate conductors, even though that this is not always true, but it's well, I guess except optical fiber, which contains no conductor, except the waveguide, which contains only one conductor. Other commonly seen transmission line types always exhibit two conductors. And somehow you will need certain dielectric material to separate the two conductors. And the imperfectness about the dielectric material, that is a very small conductivity within the dielectric, exhibit the so-called conductivity, conductance in the dielectrics. And because of this mechanism and the way it attenuates the signal, it is represented as well, you can say it's a shunt resistor in the distributed circuit, or you can express it as a conductor, conductance in the circuit. So this is the more general distributed circuit model, which is sometimes refers to as RLGC model. So you can memorize it RLGC model by drawing the series resistor, series inductor, shunt conductor, shunt capacitor to memorize the so-called RLGC model for the distributed circuit. And as I remarked on the slides, the difference between the series inductor and shunt capacitor with respect to the series resistor and shunt capacitor is what? Is the way they handle the energy. All right? The shunt capacitor and series inductor store their storage for energy. They do not dissipate energy. They only store the energy. On the other hand, on the series resistor and the shunt conductor, as there are currents or voltage drop appears across the resistance, the current goes into the resistance, they exhibit certain amount of loss, certain amount of energy loss within the resistor, within the conductor. Okay, so that's the most fundamental mechanism that when it comes to the loss of transmission line. 好啦，真的没问题。所以在这一节里头，我们要谈的就是传输线上面的耗损。之前我们谈的传输线里头 ，LC model 里头没有谈到耗损，但事实上所有的传输线都是有耗损的，所以这个耗损的机制考量进来，就变成所谓的 RLGC model， 像这边所画的，或者我黑板上所画的，所以 R 代表的是后层传输线的导体上面的 resistance， 它的电阻，而那个 ，E 呢指的是也是结构上面你可以看到的支撑这一个传输线结构，你有一些介链材料，而这介链材料它即便是天然界里头最好的绝缘体是什么？知不知道？最好的绝缘体材料是云母啊，它的那个导电性大概是一般塑胶材料的少10的6次方啊，所以非常非常低的啊。但即便是如此绝缘的材料，它的导电性也不是0啊，所以只要它有导电性，它就会有漏电流啊，所以它们就会造成这个耗损。所以在传输线上面走讯号的时候，就会造成耗损啊。同样类似的这种漏电流其实在哪一个领域也很重要？半导体啦，对不对？在半导体里头，你想想看，我们现在在谈的那个半导体的电晶体，它的那个什么几纳米啊，还是0.14个纳米1.4不是0.14啊，0.14是你们再过10年吧1.4纳米啊，还是1.6纳米的那个结构它的那个，当然啊，传统定义那个指的是什么？指的是那个 CMOS 的那个 gate 到 drain 的那个绝缘层的那个厚度那你想想看，那个厚度已经小到是一个原子结构大小的一层原子结构大小的时候只要有1咪咪的漏电流，就有可能让它的电晶体的那个操作特性产生改变OK， 所以要么是勒坏了，要么是坏掉，要么就有额外的耗损好，所以这两个造成传输线上耗损的机制请你搞清楚 ，OK And because they are originated from 2 different mechanisms, so they are remarked on the transmission line in terms of series resistor and the shunt conductor, shunt resistor. They are representing different part of the distributed circuit model. Okay, so and also note that in the figure on the textbooks, the labeling of the distributed circuit is more accurate. So the resistance here is the per unit length resistance times the length of the transmission line. So it's labeled as R delta Z, and the same principle is applied to the other 3 components. Per unit length inductance times the length of the transmission line, per unit length conductance, per unit length capacitance. Alright? Okay, so what next? Alright, so since we already introduced the 2 lacing mechanisms, the resistance on the conductors and the conductance on the dielectric, the corresponding transmission line circuit which address the voltage drop or the current difference across a small section of the transmission line should be modified accordingly. So on the top is the voltage drop description. So take a look at the parameter to the left. The first voltage is the voltage at which position? Z plus delta Z. So that's the location to the right over here. And the second term on the left is the voltage at the left. Voltage at position Z. At the same time instant t. So the voltage difference between the left and the right of this transmission line section equals to what? Equals to the voltage drop incurred on the 2 series components, the series resistor and the series inductor. Now, so the voltage drop corresponding to the series resistor will be the resistance, that is R times delta Z times what? Times the current, times the current. So you have R delta Z times I at the position Z and times 10 T. And it's exhibit a voltage drop. So you have a minus sign at the front. And the second term is the voltage drop due to the inductor. So it's minus L times delta Z times the time derivative of the current, that is del I over del T. Alright? So the first equation, we adopt the voltage drop due to the series resistance. So that's the first transmission line equation. The second transmission line equation, which addresses the current difference to the left and to the right of this transmission line section. So the difference, that is I at Z plus delta Z minus I at Z equals to what? That will be, the first term will be the current goes to the right at the right end, and the second term is the current goes to the right at the left end. And what is the difference between this current to the right and this current to the left? There will be the current goes to the ground through the two shunt element. So we need to write out the current representation that goes to the ground within this section. So that equals to minus G, the conductance, times delta Z, the conductance, times the voltage drop at this point, V times V at ZT, minus there will be the corresponding currents take place within this capacitor. So that is minus C times delta Z times the time derivative of the voltage. Alright, so we modify the transmission line equation. In chapter 6.3, we don't have the two terms. We only have the inductance and capacitance. Now, since we need to account for the loss due to resistance and conductance in the dielectric, we need to provide the two additional terms in the representation of transmission line circuit, transmission line equation. All right. So in this figure, you can see the red dash box represents the two additional loss mechanism imposed on the transmission line equation. Note that equation 7.63 A and B are the so-called transmission line voltage and transmission line currents in what form? In instantaneous form. So that's the actual representation of voltage and currents on the transmission line. And for our convenience, for the convenience of do the derivation or write up the equation, it's a common practice to write up the transmission line equation in terms of phasor format. So as we already learned that by omit the time dependence, because we already assume the signal that goes in the transmission line is in the form of a sinusoidal signal, and it belongs to a specific frequency. 所以我们默认当在传输线上面走的讯号是特定频率的正弦波讯号的时候，我们在写这一个传输线关系式的时候，就我们偷懒一点，就把它从 instantaneous form 改写成所谓的 phasor form。所以你会看到下面的 7.64 就是 phasor form， 所以跟 7.63 的 instantaneous form 相比有什么差异？你没有看到小 t 了，对不对？ 你没有看到小 t 的那个描述了哈。原来的 7.63 的话，你会看到你的传输线上面的电压、电流都是 functions of voltage and function of time， 但在不是 function of voltage，function of frequency and function of time。但在 7.64AB 的时候呢，你只会看到它是 function of frequency 啊，不过它那个 function of frequency 也看得很隐晦啊，在这里啊 omega 是你的频率啊，然后那个 function of time 的这件事情就藏起来了啊。他们其实是要补上一个 term 叫做 exponential j omega t 嘛，我们之前有看过啊，那个东西大家约定俗成不要写了啊，不然呢每一个 term 都要写一个 exponential j omega t， 太过啰嗦，太过麻烦啊，所以他们恭候闷下啊，只有在遇到微分或积分的时候，你每微一次你就会甩出一个 j omega 出来，因为那个 exponential j omega t 那个 time dependence， 你在做时间的微分的时候，你就会甩一个 j omega 出来嘛。好，那相对的，你在积分的时候，你要还给他一个 j omega。好，所以phasor form 的那个 transmissional equation 也要做对应的改写了哈，也就是说，左边是。你看啊 ，transmissional equation 怎么记嘛？左边是空间微分嘛，右边是时间微分。但 phasor form 的时候，时间微分就变成是 j omega。但因为第一项的那个 loss 那个 term 哈，跟时间无关，它是瞬间即得的哈，它基本上都是 v 跟 i 的关系或 i 跟 v 的关系啊，所以直接就变成负的 ri 负的 gv。好，所以下面的话是 phasor form 的。在考虑的传输线上耗损的 phasor form 的表现样子啊 ，equation 变成是 7.64AB。Alright, combining the two transmissional equations by eliminating the current I, we can obtain the so-called wave equation. So use this opportunity, we try to demonstrate the derivation of wave equation again. So to do that, you kind of use the two transmissional equation jointly by substitute I with this representation. So we can begin with 764 by taking an extra spatial derivation of v over the line direction z. So you take del over del z again on both sides. Okay, so to the left-hand side, at the left-hand side, it simply becomes second-order derivative of v with respect to the position z. And to the right, you have not only originally you have a time derivative of the current I, and now you have a spatial derivative of I with respect to z. Then you can identify this term with 7.64 by substitute the right-hand side of this equation into the original equation. So now it becomes the so-called second-order equation 二次偏微分方程式，电压的二次偏微分方程式所以下面这个式子你会看到，这个是电压的二次空间偏微分。右边这一个嘞，等号右边这个嘞，有没有偏微分？看起来没有啊，但实际上你要看它其实是什么？它是 v 的电压讯号对时间的二次偏微分。为什么？因为它会有一个 omega 的平方事实上这边是有2次的 omega 在里头，所以其实等号的右边的那个电压项，它其实是有2次的时间偏微分的所以二次偏微分方程式里头同时包含有对时间的二次偏微分以及对空间的二次偏微分的描述的话，它就可以形成一个波动方程式的形式波动方程式的形式。所以整理一下这个式子呢，你可以看到 你可以 identify 它是 7.65 的形式啊，也就是等号左边是空间的二次边微分，等号右边呢，它其实是时间的二次边微分，只是它偏微分的结果我们用 gamma to the square 来去表示它 ，OK？ And the gamma to the square can be identified as the square of the so-called propagation constant. Alright， 这边回忆一下啦，伽马叫做什么？伽马的定义叫做什么 ？propagation constant. And by definition, gamma 不是 r， 这边是伽马 equals to alpha plus j beta. Alpha is referred to as what? Attenuation constant, 耗损常数。Beta is known as the phase constant, 相位常数，耗损常数，相位常数。And know that both alpha and beta are positive real number， 它们都是正实数。正常来讲，都是正实数。哦，我说，老师，既然你强调正常，那是不是有不正常的？对啊，哦，天然的材料都是正常的，都是阿拉跟贝塔都是正实数的啊、哦。但你假如人格比较扭曲的话，你就可以造出一些不正常的传输线啊。比如说阿拉跟贝塔就不保证是正实数了啊、哦。OK。Alright, so by definition, because alpha and beta are real positive number, so gamma is a complex number. And as you can see, since alpha is referred to as the attenuation constant, so it's of course, by the name suggests, is closely related to loss. So if alpha equals to 0, then this transmission line, the propagation constant of the transmission line become a pure imaginary number. Then it has no attenuation term, which means it's a lossless transmission line. So if alpha equals to 0, then the wave equation becomes the second order derivative of V equals to minus beta to the square V. And this is referred to as the lossless transmission line, the wave equation of a lossless transmission line. On the other hand, if alpha is non-zero, is a positive real number, then the gamma, the propagation constant, described the loss and phase change of the signal that go into this low C transmission line. Okay. Alright, so equation 7.66, the box down below is the propagation constant of the wave in a low C transmission line. The first one, alpha, is the attenuation constant. The second, beta, is the phase constant, 相位常数 And with the help of the propagation constant, the solution, the general formula of the solution of the voltage signal reside within the transmission line can be written as 7.67. That is, the voltage on a specific position on the transmission line, say Z, equals to A times exponential minus gamma Z plus B times exponential gamma Z. So as we have seen this for many of signal expression on the transmission line for several times, we know that the two terms represents what? The first term represents the components of the signal that's going to the right on the transmission line, while the second term describes the signal that's going to the left. So you notice that there is a sign difference in the index of the exponential. One is exponential minus gamma Z, while the other one is exponential gamma Z. Okay, so they share the same propagation constant because they are going on the same transmission line. However, the wave propagation direction are different. The first one goes to the right, so it has exponential minus gamma z dependence. And the second one goes to the left. And A and B are the description about the magnitude and phase of the two components. So not that A and B are not necessarily real number. They are in general complex number. So A and B may be different in magnitude and different in phase as well. Alright? So they are constant, but they are complex number. Or otherwise you can, no, not otherwise. Okay. Right, so in the middle, the equation is the equation in the middle is the voltage on the transmission line expressed in instantaneous form. 所以上面是 phasor form 中间那个是 instantaneous form。因为什么？因为你有看到 t 了嘛，对不对？上面的 phasor form 你看不到 t， 但中间的那个式子你可以看得到 t， 所以它是 instantaneous form。那 phasor form 到 instantaneous form 的转换你要记起来哦，把 phasor form 乘上 exponential j omega t， 然后再取10步所以你会看到它补上了什么东西？它补上了这一项 exponential j omega t， exponential j omega t， 然后再取10步然后这个是原来的 a。只是说它现在把它的 magnitude 跟它的相角分开，变成 a exponential j theta， b 又变成 a b 乘上 exponential j phi，alright？ 其他是把 exponential minus gamma z 拆成 exponential minus alpha z 跟 exponential minus j beta z， 这边应该有个负号了那个slide上面没有很清楚，你自己看一下，没有的话把它补上去。minus j beta z 后面那个都是正的啦 ，exponential alpha z 跟 exponential j beta z。好啦，这边你看到有4个 exponential 嘛，对不对？但是因为我们要取10步，所以你稍微瞄一下这4个 exponential， 有3个跟其他1个不一样，对不对？有1个跟其他3个不一样那个阿尔法的话呢，它的指数是纯实数，对不对？所以要单独处理。那这一个呢，第1个、第2、第3个、第4个呢，它都是纯虚数那个指数都是纯虚数嘛，一个 j theta， 一个 j omega t， 还有一个 j beta t， 所以那个有 j 的就可以聚在一起exponential j blah 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 取10步之后就变成是 cosine 的这3个项cosine 把这3个项的那个指数可以用 cosine 来表示，所以就 omega t 减 beta z 加 theta， 这边是 omega t 加 beta z， 为什么？因为是正的加 phi 所以原本的那个式子里头虚部的地方就变成是 cosine那10步的地方就提出来嘛 ，a exponential minus alpha z 跟b exponential alpha z 所以在看这2项的时候要记得，第一项还是往右走的，第2项还是往左走的所以你会看到 exponential minus alpha z， 第一项是 exponential minus alpha z， 第2项呢是 exponential 正的 alpha z， 这2个的差别在哪里？这2个的差别在注意因为 alpha 是一个正实数，所以第一项告诉你 z 越大。z 是越大嘛？对 ，z 越大了，它的 exponential 负 alpha z 那个 alpha z 越大，它负的越大，它就会越小。所以第一项 exponential 负 alpha z 它给予第一项的特性就是随着 z 的增加，越往右边走，它的讯号会越来越小。Okay? So the magnitude of the signal of the first term, as it goes further to the right, the magnitude becomes smaller and smaller. because you have a positive, you are going to the positive z direction, and alpha is a positive real number. So as the product of alpha z becomes larger and larger, then exponential minus alpha z term becomes smaller and smaller, which is consistent with the fact that the signal becomes smaller and smaller due to the presence of loss on the transmission line. On the other hand, the second term, which goes from right to the left, so its attenuation term is labeled as exponential positive alpha z. So as z becomes smaller and smaller, which means the signal goes from right to left, the signal also becomes smaller and smaller. Because alpha z number becomes smaller and smaller. So that's also consistent with the fact that the signal on the transmission line the energy dwindles. The energy becomes smaller and smaller as it propagates along the transmission line. Alright, so equation 7.60 is the general expression in which form? Phasor form, for the transmission line signal on the line, right? So you have V plus and V minus, which represents the component that goes to the right and the component goes to the left. Okay? So here are some description about the propagation constant. The quantity beta, which is the imaginary part of the propagation constant gamma, is, of course, the phase constant. Represents the rate of change of phase with z for a fixed time. At a specific time, the phase are different at a position z, at a different location on the transmission line. The quantity alpha, which is the real power of the propagation constant gamma, is the attenuation constant, 耗损常数, denoting that the waves gets attenuated by the factor of exponential alpha per unit distance as they propagate in the respective direction, which can be either positive z direction or the negative z direction. So gamma, again, is the so-called propagation constant. And the unit for alpha is unit per meter. No, meters per meter. Well, actually, in the question of the textbooks, sometimes alpha are labeled in terms of meters per wavelength. Well, anyway, alpha 都是一个单位长度的耗损。所以有的这个要小心一点看题目的描述，它有没有特指说它这个 alpha 是 meter per meter 或者是 meter per wavelength 我们等一下会有例题啦但你在例题的时候就要稍微留意一下 alpha 的单位是什么。它告诉你的 alpha 说 alpha 每经过一个波长它会耗损多少，或者是每经过1公尺它会耗损多少用 meter per wavelength 比较精确一点因为不同频率的讯号波长不同，所以只要你用 meter per meter 来去描述的话，那不同频率的它的 alpha 值会有比较大的差异后来Now that we have introduced the idea of loss mechanism within the transmission line, let's revisit the key parameter about the transmission line, which are what? One is the characteristic impedance, 特征阻抗the other is characteristic impedance 跟啥？propagation propagation constant 嘛 ，OK 哈，所以你会看到右下方的那个是 propagation constant 嘛 ，gamma by definition 是 alpha 加 beta 加 j beta 啊，那用 RLGC model 的话就变成是一个 R 加 j omega L 乘上 G 加 j omega C 开根号哈，其实原始是什么？原始是那个 LC 开根号乘 J 嘛哈，对啊，哦，但这个。但变成 RLGC model 之后，那个 gamma 就变得比较复杂啊。那另外是它的那个 characteristic impedance， 还记得在 lossless case 的时候，那个 Z 等于什么 ？characteristic impedance 等于什么？等于 square root of L plus over C 嘛，对不对？但这边的时候 with loss it becomes square root of R plus J omega L divided by G plus J omega C 啊，所以假如 R 等于0 ，G 等于0的话，那这一个 characteristic impedance 又会变回去原来的啊。但假如你要把耗损考虑进去的话呢，你的 characteristic impedance 特征阻抗的表示式就会特性阻抗、特征阻抗的表示式就会变得比较复杂啊。它会跟你的耗损的 R 跟 G 有关，也会跟什么有关？频率有关。好。Alright, so this slide kind of summarizes what we have discussed so far. You have the voltage description on the transmission line, which is dedicated for the description of lossy transmission line, and this equation is the current equation on the transmission line, which is also taken into account of the lossy mechanism. So you see the propagation constant gamma is taken into account in these two equations. And the associated propagation constant and characteristic impedance should be modified to take into account R and G, and as well as frequency omega in the two equations. Alright, and let's discuss a little bit about the parameters. So we see that gamma, the propagation constant, 记起来了没有？ gamma 等于什么？ alpha 加 j beta 嘛，对不对？然后呢，它又等于什么 ？R 加上 j omega L 乘上 G 加上 j omega C 的乘积所以你会看到，在这一个式子里头，你有这个好几项RLGC model 4项，哪个比较好得到？哪个比较好得到？从数学式上面看出来，你会觉得 RLGC 比较容易了哈。如果 RLGC 只知道的话，你的那个 alpha 跟 beta 就可以算出来 ，gamma 也可以算出来嘛哈。但实物上面 ，RLGC 不是常数对于传输线，对于材料来讲，它做成材料做成传输线之后做成一个传输线结构之后，它的单位长的电阻、单位长的电感、单位长的电容、单位长的电导，会随频率变化，会有一定的 time dependence， 会有一定的 frequency dependence， 通常不是很剧烈啦，所以假如你关心的那个讯号是一个不是太宽频的讯号，是一个窄频的讯号的话，那其实 RLGC 还是可以用常数来去代表的但一个更 general 的 picture 就是说你有兴趣的频宽够大的时候 ，RLGC 不是常数，所以不是定值，不是常数，它是频率的函数的frequency of they are function of frequencies. So in reality, in actual scenarios, it's more convenient to do measurements on the transmission line. And according to the measurement result, we can determine the propagation constant, which can be transformed into the attenuation constant alpha and beta. And with the calculated alpha and beta, you can you can find the corresponding RLGC values for this specific transmission line at the specified frequency 所以在实物上面的话，其实比较常看到的做法是用实验的方式，也就是你真的拿那个材料跟这个传输线结构去做一段传输线出来，然后对它做一些基本的测试，比如说量测它的反射系数，量测它的传输系数，然后根据这些量测的结果，我们可以转换算出来它所对应的 RLGC 值所以这个是实物上面比较常看到的做法So in practice, this quantity are obtained from experimental determination of characteristic impedance and propagation constant. Well, next we will look at the lossy transmission line again from an interesting perspective. That is, assuming the loss in the transmission line is small. If this assumption is true, that the loss in the transmission line is not that significant, what happens with the result? Okay, and the discussion here is important because it's close to actual scenario. In the actual transmission line design, the microwave circuit design, of course, you will not fabricate or manufacture a very lossy transmission line, right? You know that the purpose, the objective of a transmission line is to deliver energy, to transmit energy. So the loss on the transmission line should be minimized. The loss should be, the smaller the loss, the better the transmission line, right? So the assumption here, that is, low loss transmission line is usually the case. Low loss transmission line. So based on the assumption that the loss is small on the transmission line, what happens? Well, as you can see, here. The characteristic impedance here is kind of complicated, and is that a real number? If this is lossless, then this is a real number. If R and G are relatively large or cannot be neglected, this is a complex number. Which means what? If this is a complex number, what is significance? What is the implication of this result? Then this result suggests the voltage and the current are not in phase in the specific point of the transmission line. 对了，所以你会看到，假如那个 R 值啊、G 值啊够大的话，你的那个，你连 characteristic impedance 都会变成 complex number 那你的讯号的描述，在传输线里的讯号描述就会变得很复杂。那这边我们导入一个假设，叫做低耗损的传输线 （low loss 的 transmission line）。然后你会发现，把 low loss 传输线的假设成立的话，那其实它的结果跟无耗损传输线几乎差不多了我们先偷看一下答案了So if you take a sneak preview about the result, once the assumption of low loss transmission line is true, then here is the phase constant, beta. Well, it's actually nearly the same as the one of lossless transmission line. It's the same as omega times square root of L times C. Here is the propagation velocity. If it's a lossy transmission line, the propagation velocity is a complex number. Can you imagine the implication of that? No, it's probably hard to imagine, right? Hard to describe, Unfortunately, most of the time, usually, if the low loss transmission line assumption is true, then VP is about the same as the lossless case, which can be expressed, which by definition is omega over beta. And because beta can be approximated as this number, then it's roughly the same as 1 over square root of L and C, L times C. So the VP, the propagation velocity, the phase constant are about the same as lossless transmission line. The only thing that you cannot ignore is the attenuation constant alpha, which is directly related to R and G value, and they can be ignored. Otherwise, this is a lossless transmission line, not a lossy transmission line. Okay. However, you can, let me finish this part. So here is the actual description about the propagation constant gamma. However, you can see that the first part and the second part, which is R plus J omega L and G plus J omega C, are modified a little bit. And by assuming that R is small, G is small, so the second term over here is relatively small. Now that this relationship, 这边请你看好哦，我们会用到这个关系式好多好多遍。在电磁学里头，我们用这个关系式好多好多遍。1加 x 的 n 次方加 x 够小，接近 x 接近0的话，那1加 x 的 n 次方可以被简化或改写成1加 nx。所以这边本来是1加上这个的这个东西所以就变成是直接变成这一项。这边其实是这两项乘上这两项嘛，对不对？当然我们的假设是这一项已经够小了，这一项已经够小，所以它们两相乘变得小的又小，所以本来是4项的，简化之后变成3项，有没有？然后呢，我们在这里头用这个关系式，所以它变成是这个的开根号跟这个的开根号好，所以你会看到这边是等号哦，但这边的话，我们4项变3项，所以变成是约等于，这边再约等于1次，这边再约等于1次，所以这一个前面整理完之后，这个是它的贝塔 phase constant， 这个是实部，这个是 attenuation constant， 你会看到这是实数后面那个是虚数，这是实数，所以它代表的是 alpha， 也就是你的 attenuation constant 耗损的部分所以耗损必须要被考量进去假如你是 low loss transmission line 的话，alpha 必须被考量进去，但是贝塔跟 VP 波数跟相位常数跟原来的是差不多的。OK， 我们休息一下。